informal proofs are correct, or at least they're not very clear. So this is a kind of summary of the various bits of my talk. So really, most of my talk is in the third section, so I'll be fairly brief about the others and skip over a lot of details. So this picture of Andrei was taken in Cambridge. So just after my... So I first visited Białystok because of the QED workshop. And Bob Boyle had told us about this mysterious system called MESA that nobody in the West really knew anything about. And so, as well as attending the conference, one thing I was very interested in doing was finding out more about MESA. And Andrei himself was willing to actually help me and a few other people, like Randall Holmes and Paul Jackson. And he didn't just talk to us about MESA and present MESA, he actually gave us hand-on demo sessions. So we would sit in the university for a few hours a day, typing on our PCs. I think it was the first time in my life I'd ever used Windows, actually, and learned how to construct MESA articles. And for me, it was a very exciting and also somewhat chastening experience. Exciting and chastening both for the same reasons. MESA seemed to be remarkably easy to use compared with HAL, which was the system I was using at the time. And so in particular, I was very impressed with the MESA proof language, and for that reason I then went on to write a version of MESA as proof language for HAL, and then lots of other people did the same thing. And now, for example, we have Isabel Issa, so we now have many people copying MESA's proof style. What we don't have is so many people copying MESA's type system, but one can argue, in fact, that more people should be.
Well, Guntia is doing it, right? Like the whole canonical structure, Phi Thompson stuff is to a large extent.
In some sense, yes, it is a sort of type system in some sense, yeah, even though they also have foundational types. Yeah. So after the QED workshop, Andrei and I traveled to Cambridge together, where I was able to sort of take him to the computer lab and introduce him to Mike Gordon. That's also where the picture that we saw in Arto's talk was taken, where Mike and Robin Milner were all together. And this was taken by the River Cam. I guess this shows Andrei in his natural environment, drinking just enough beer so that he was productive at formalization, because he always used to say about 2 beers was optimal, because that just relaxed you enough without starting to make you confused. But then he had much higher capacity for alcohol than many of us. And you see he actually has a plastic glass because it was such a nice day, they'd run out of glasses. It's not because we drank so much. And here's another picture. So this is Andrei on the left and me as a young man on the middle. And there's Mike Gordon again falling asleep. So this is taken from my office. So it was really a marvelous experience that certainly for me was a formative moment intellectually. It also, I think, had a tremendous impact because of the way it helped to spread MESA's ideas in other places. So it's just after Andrei's visit to Cambridge and the work I was doing, lots of people started copying the MESA proof style. So it was a very, very important occasion, I think.
So when was this exactly? Which year?
I think it was 95.
So it was before the Warsaw QED workshop or after?
It was just after.
Okay.
Yes. Yes, I think it was 95, because I remember when I was here last time, the zloty was being changed from old zlotys to new zlotys, which were a factor of 10 to the 4 different. And I was totally confused every time I went to the shop, because all the shops had already started counting things in units of 1,000. And some of them were labeled in old zlotys divided by 1,000, and some were in new zlotys. So basically, I never knew whether something was 3 times as expensive as at home or 3 times as cheap. Yeah. But it was fun. It's very nice to be back. Since I'm reminiscing, I wanted to take the reminiscences back just another generation to Andrei's PhD advisor, Borsuk. I can't promise to have taken this picture. I just picked it up. I think it was taken by Hans, actually. I just picked it up off the web. So I wanted to show you, I've been having fun formalizing some of Borsuk's So I just wanted to show you some of the kind of formal theorems that I've got. They maybe don't look very appealing because I'm actually showing you the raw whole-light syntax. But this, for example, is the famous homotopy extension theorem. So this is sometimes called the top hat theorem because it's kind of saying if you have a function that's homotopic to another function and you can extend the function at one end of that homotopy, then you can extend the entire homotopy. So that's basically what this is saying with a bunch of side conditions. So it's saying if you have a homotopy between f and g, which are functions from s to u, and f has an extension to a continuous function over t, then g also has an extension to a continuous function of t, and so on. And we have some side condition that u is an absolute neighborhood retract, or else both of the domains are absolute neighborhood retracts, something like that. So this is a really nice theorem. It's used all over the place in the whole-light topology theory. And then there's this really nice theorem, which is a characterization of when a compact set separates Euclidean space. The nice thing is it's completely homotopic. It's a homotopic characterization. This isn't quite as clear as you'd expect because one-dimensional space is different from every other dimensional space in the sense that a contractible set does actually separate one-dimensional space, right, because you can't sort of get around it. So rather than stating it in terms of separation, it's stated in terms of having the complement having no bounded component. So it basically says if you have a compact set S, its complement, all the components of its complement are unbounded if and only if some homotopic thing, mappings into spheres are true. And so the wonderful thing about this is it then gives you very easily this really simple theorem that if you have two compact subsets of n-dimensional Euclidean space that are homotopy equivalent, then one of them separates space if and only if the other one separates space. So this is really a very elegant result. So I think out of all the theorems I formalized, this is one of my favorites because it's very crisp and clean. And of course, in particular, it gives you part of the Jordan theorem in a more general context. It doesn't tell you how many components the complement has, but it does at least tell you if you have any set S that's homeomorphic to a non-trivial sphere, then the complement is disconnected. So anyway, I couldn't resist showing you that, just to show you some theorems that are easy to formalize. So now we come on to the main topic of my talk, which is about something that's maybe, on the face of it at least, not so easy to formalize. So there are a lot of algorithms that kind of generally belong in the sort of symbolic computation computer algebra world that are very good at proving quite complicated formulas involving summations. I'll give you some examples and a bit more precise definition of the domain later. So the first one really is due to Bill Gosper in the 1970s, which was his algorithm for hypergeometric antidifferences. I'll explain that in more detail in the next slide. And Zeilberger has a very general algorithm for proving certain properties of so-called holonomic sequences, which are basically sequences that satisfy a recurrence relation with polynomial coefficients. For a simpler case of so-called hypergeometric sums, there's a much simpler algorithm due to Wilf and Zeilberger, which is commonly just known as WZ, or WZ if you're not American. And that's mainly what I'm going to be interested in formalizing. But I'm also going to discuss Gosper's algorithm because Gosper's algorithm appears as a component of the WZ algorithm. And a good reference is this nice book called A equals B, which is by, well, I'm not sure I trust myself to pronounce his name, but Petkovšek, thank you. Wilf and Zeilberger. So it's a very nice read. It has lots of nice examples and all sorts of interesting reflections and tells you about the history. But having said that, when I came to formalize it, I started to look at it with new eyes and started to realize that it's also, in my opinion, also quite non-rigorous. So I'll explain what I mean later. So first, I'm going to use the notion of a hypergeometric sequence. So just to make it clear, let me define once and for all what I mean by a hypergeometric sequence. So I'm thinking of sequences of real numbers here, but you could think of them as any field, basically. So it's basically just a sequence of real numbers where the ratio of successive terms, the n plus 1th term divided by the nth term, is a rational function of n. In other words, it's the quotient of two non-trivial whole numbers. So for example, the factorial function is hypergeometric because the n plus 1th term is n plus 1 times the nth term, which is a rational function indeed, it's a polynomial. And similarly, power of 2 function is also hypergeometric for the same reason. And when we talk about functions of more than one variable, when you say they're hypergeometric, what that normally means is if you fix all but one variable, they're hypergeometric in the other variables. So, for example, we're going to say binomial coefficients are hypergeometric because they satisfy these recurrence relations. So that's the basic domain of what I'm talking about, these so-called hypergeometric sequences. So as you can see, it's a pretty general notion. It includes a lot of obvious sequences that you would first think of. And the first really interesting result in this area is Gosper's algorithm. So what Gosper's algorithm does is it takes a hypergeometric term. I don't want to get into exactly how you specify a hypergeometric term, but anyway, some specification of a hypergeometric term. The algorithm will do one of two things. It will either return a hypergeometric antidifference, in other words, some other hypergeometric term S, such that the difference of successive S terms is equal to k, for all k. When I write these parameterized things, that's usually an implicit universal quantifier over k. So either it will do that, or it will fail. But the failure doesn't just mean it didn't do a good job. It actually means there is no hypergeometric antidifference. So you can actually learn some definite facts from when the algorithm fails. So I don't want to talk about how the algorithm works. It's, fairly classic symbolic computation type stuff. Let me just give you an example. Oh, sorry, one thing I also wanted to say is one of the interesting things about an antidifference is that it also lets you solve a definite summation. Because if you want to sum this hypergeometric term from A to B, then if you have an antidifference, then if you imagine taking that sum, all the adjacent positive and negative terms cancel, and you're just left with the first term and the last term, so you basically end up with that. So this is very much analogous with doing integrals using the fundamental theorem of calculus. So this is the kind of discrete analog of the fundamental theorem of calculus. I hope that doesn't matter whether it's... Okay. Now actually, if Gosper's algorithm finds, if you do have two sequences that are related by this, and the antidifference is in fact hypergeometric, then it's not very difficult to show that actually S and T are a rational function multiple of each other, and therefore that T is also hypergeometric. So in other words, if you have this relationship, and S is hypergeometric, it implies that T is hypergeometric. But as I noted, the converse is not true. Certain hypergeometric T's don't have a hypergeometric antidifference. So let's look at an example. So here's a slightly complicated hypergeometric term. So it's k times k factorial over n to the k times n choose k. And so let's see what Gosper's algorithm has to say about it. I'm going to use the implementation in Maxima by Fabrizio Caruso just because it's free and I happen to have a copy. So you ask it for the antidifference of that term, and it just tells you the answer. Very nice. And you can actually use this to solve an American Mathematical Monthly problem. So actually someone proposed this sum, proving what the value of this sum was as problem 3088 in the American Mathematical Monthly. And using Gosper's algorithm, it's basically automatic. The only thing you need to do is compute S n plus 1 minus S1. And that's pretty obvious because when you set k equal to n plus 1, this collapses to 0, so this term is 0. And similarly, it's easy to see this one comes out to minus n. So it's a very nice way of solving problems. If only work, and that's what motivates the step to the WZ algorithm. So, in what follows, I'm going to explicitly consider functions of two integer variables, or arguably natural number variables, n and k. I want to make the parameterization explicit because it makes certain things clear. I'm also going to kind of ignore, for the most part, the limits of summation and just assume I'm summing it over all integers. This is the way a equals b presents it. The intuition being that the function has finite support, so if you sum it over all integers, you're really summing it over some finite segment. So for example, with this one, this thing collapses to 0 except for k in the range 0 to n. So we're assuming for every n this thing has finite support with respect to k. And so we often ignore the limits of summation and just say we sum it over all integers. So as we noticed, even if a hypergeometric term does have a well-defined and even hypergeometric definite sum, Gosper's algorithm might tell us that it has no antidifference or indefinite sum, if you like. But this applies even to this really trivial example. So if you just want to sum, we did quite a complicated example by Gosper's algorithm, so you might think, well, this one will be easy. But actually, this one doesn't work with Gosper's algorithm. There's no hypergeometric antidifference. Of course, it's very easy to prove it just ad hoc by just imagining it as the binomial expansion of 1 plus 1 to the n, and therefore it's really kind of easy to see that it's 2 to the n. But you can't solve this problem by Gosper's algorithm. So this is an example of where the generalization of the WZ algorithm is useful. So the basic idea of the WZ algorithm is to apply Gosper's algorithm not to f itself, but to the difference of f of n plus 1 and fn. That's the kind of basic case of the WZ algorithm. There is a more complicated case where it analyzes more complicated recurrences, but I'll ignore that for present purposes. Because all the interesting issues arise in this special case. So what's the idea? So if we have our function f, we'll say that the function g is WZ mate of f, and that they form a WZ pair, if basically they satisfy this identity. So this identity is absolutely fundamental in what follows. So this is what it means for f and g to form a WZ pair. So it means you have a kind of relationship between offsets of f and offsets of g, but the offset of f is with respect to n, and the offset of g is with respect to k. So this might look like a slightly peculiar concept. The idea of why this is useful is pretty much the same. You get the same kind of telescoping phenomenon of sums. So suppose that's true. If you imagine summing this term minus this term from a to b, then that's the same as summing the left-hand side of that equation from a to b, and therefore it's the same as summing the right-hand side from a to b, and therefore you get exactly the same kind of telescoping phenomenon. So you just get g n b plus 1 minus g n a. Okay. So far, so good. And then we're going to assume one thing that I didn't say, but perhaps I should have, is that using basically the same reasoning as we used in Gosper's algorithm, you can show that g is actually a rational function multiple of f, which means basically that if f has finite support, which was our initial assumption, then g will also have finite support. So what that means is that if we choose a and b wide enough, like a negative enough and b positive enough, both of these terms are going to collapse to 0, which means that these two terms are the same, so the result is actually independent of n. And therefore, we can just evaluate the sum at some really easy value, like 0, which is indeed usually easy. So that's the basic idea. So here's the method in more detail. This is the algorithm as presented in the book A equals B. So suppose you want to verify a sum of this form. And as I said, we're using the finite support property of of f. So we're summing over all integers. They do explicitly say integers, not natural numbers, which we'll come back to later. So the first step is to divide through by s. Well, obviously if s is 0, you don't do this, but normally you do this, right? So that means that you basically need to just prove something analogous with a special case. this difference, and you find its WZ mate. And then, as noted above, you conclude that the sum is actually independent of n, and so you just check some easy value, and you're done. So that's very nice. So let's see an example. So this example is very closely following the presentation in the book, A equals B. So, for a bit of variety, this is the sum of squares of the binomial coefficients, and we're supposed to prove that the result is 2n choose n. So the first stage in the recipe was we divided through by the right-hand side. So we're really proving this, we want to prove that this sum, fnk, is equal to 1, where fnk is just our sum divided by 2n and n, which we'll just also write as this sometimes, as it suits us. And then we apply Gossamer's algorithm, so I won't actually show you the computer algebra system doing it, but take my word for it, if you do this in computer algebra system, if you do it in the maximum implementation, it gives you this rational function as the magic certificate. And that is supposed to tell you that if you multiply f by that rational function, then that gives you the WZ mate. And then you conclude that the sum is independent of n, and so the problem is just reduced to proving it in the special case n equals 0. But that's very easy because the sum then only basically has one term, because everything except the k equals 0 term disappears. So it's very straightforward. So this looks great. It seems in order to formalize this in a theorem problem, all we need to do is have some simple lash up to a computer algebra system to give us the rational function, and all the reasoning involved is basically trivial. All the difficult stuff was done in the computer algebra system, finding the rational function. But once we've got it, all we need to do is do a bit of algebraic manipulation. And this, of course, is a standard theme in theorem proving. You know, people, for example, Laurent Terry and I once linked Hall to Maple, doing integrals by checking them as derivatives. And similarly, people have primality certificates in Coq and this sort of thing. So this fits very well into this theme. And so all we really have to do inside the theorem proof is just a very routine algebraic simplification of proving that those expressions satisfy the WZ pair property, which seems very easy. And the A equals B book explicitly says it's very easy. So they say, at this point we've arrived at something that we refer to throughout this book as a routinely verifiable identity. Okay. So that phrase means roughly that your pet chimpanzee can check out the equation. So first, cancel out all factors that look like powers that can be cancelled. Replace every binomial coefficient in sight by the quotient of factorials that it represents. Cancel out all the factorials by suitable divisions, and that just leaves you a polynomial. So that looks entirely plausible, and actually I never noticed there was anything wrong with this statement until I was forced to formalize it. But as soon as you actually have to formalize this stuff, you start to look at this with a much more critical gaze, and you start to worry. So first of all, we're supposed to be summing over all integers, but how are factorials supposed to be defined for negative integers and binomial coefficients? It's not at all clear. And indeed, it's not clear at all why it's valid to replace binomial coefficients with quotient of factorials that it represents, because by definition, I mean, using the combinatorial definition of n choose k, this is actually 0 except for k in the range 0 to n. And this is not obviously 0. Indeed, it's not even obviously well defined, because, you know, are we doing integer subtraction and taking negative factorials, so what are we actually doing? And then this lovely rational function that we get actually has poles where the denominator becomes 0. Now you might think, okay, in principle it has poles, but the argument doesn't really depend on that. Unfortunately, the argument does always critically depend on summing it through one of its poles, which is a bit unfortunate. So, all in all, it actually seems extremely difficult on the naive interpretation of what the book A equals B says to determine that it's actually right. That's not to say there isn't something correct there. It's just what is correct is not really what they're stating, right? So yeah, it's quite puzzling. And I'm not the only person to notice this. So there was a nice talk on formalizing in Coq the irrationality of zeta 3, where they're doing some analogous telescoping combinations using computer algebra systems. And to avoid the poles of the rational function, they basically ended up taking a whole bunch of terms out of the sum manually and adding them back to avoid summing this thing over the poles. And similarly, I've heard of at least one person who tried to formalize this stuff, realized how incomprehensible it was, and gave up. So it's an interesting situation. On the face of it, doesn't seem very easy to formalize. But, I mean, on the positive side, that means formalization can make a contribution. Maybe by formalizing it, we can actually also explain it and say what the semantics is. So,
have you tried to ask Doron Zeilberger about it?
No, I haven't yet. Perhaps I should.
Do you know his opinions about formalization?
I know that his opinions about formalization are not fulsome. Yes. So in order to, I mean, I should say there are other presentations of the WZ method that do give an interpretation that's a bit like what I'm talking about here. So this isn't completely unknown. It's just that this is kind of folk knowledge in the community of people who do this sort of thing. And if you look at most of the standard presentations, you would never see this. You know, it's also in the concrete mathematics book by Knuth and et al. And I've never seen anything rigorous there about these issues either, and a whole lot of other places. But you can find research papers that seem at least implicitly aware of this issue. So for inspiration, I want to just look briefly at another proof in whole light, which is the proof of Sylvester's determinant identity. This might look like a very dramatic change of domain, but you'll see the connection in a moment. So Sylvester's determinant identity says that if you have two matrices A and B, then the determinant of the identity matrix plus AB is actually equal to the determinant of the identity matrix plus BA. Now, there are many ways of proving this, but the proof that I think is simplest is the following. First of all, it's fairly easy to assume that the matrices are square by kind of padding them out with ones and zeros. That's a bit boring, I won't go into that. So let's suppose the matrices are square. Then we just observe, using the product rule for determinants, that the determinant of I plus AB times the determinant of A is equal to the determinant of their products, A plus AB, and then we just factor it the other way, use the determinants property again, and then we just get the result by cancelling get A from both sides. Which is fine, except, unfortunately, the determinant of A might be 0. So this looks a bit like the same sort of problem, where we have something that looks like a very simple, clean, intuitive proof, but it's not quite right because of dividing by 0. So what I used in whole light to argue this is a kind of limit argument. So first I proved that every matrix can be approximated arbitrarily closely by an invertible matrix. That's pretty easy to prove. It's not that you just follow your nose. And then you can use a kind of limit argument because basically the determinant of I plus AB minus the determinant of I plus BA is basically a continuous function of the two matrices. So it's sufficient to show that it holds for, in some sense, a generic matrix that tends to the ones you actually care about. Okay. So this is quite a nice argument. So, and this occurs all over the place, like in algebraic geometry and so on. You want to prove something for a sort of generic object to avoid some pathologies of specific cases. So what we want to do is do the same sort of thing with the WZ algorithm. Understand it as a limit in some sense, so that it's coherent to apply all these naive simplifications. So the trouble is, in order to generalize it, we need to generalize factorials to gamma functions. So just a reminder about the gamma function. It's basically a generalization of the factorial function, except, I guess largely for historical reasons, it's offset by 1, so gamma of n plus 1 is actually n factorial. And this is what the graph of the real gamma function looks like. So on the right-hand side of the real line, it's just a very nicely behaved generalization of well defined almost everywhere, but it has singularities at the negative integers, so it shoots off to either positive infinity or negative infinity at negative integers. So formalization of the gamma function is an interesting thing in itself. I mean, I could easily give a 15-minute talk about that, but I'll just give you one slide. So I start by defining the complex gamma function using a limit. It's common to see it defined using an integral, but the trouble with that is that it's only valid in certain domains, and then you have to do analytic continuation. It gets a bit messy, so it's easier just to take this as the definition. This is what it looks like in Hull. It looks kind of disgusting, actually, because Hull's putting in a lot of explicit typecast. So the ampersand in this statement is the typecast from natural numbers to reals, and then CX is the typecast from reals to complex numbers. So 0 is actually CX ampersand 0. So it looks a bit ugly, but I mean it's just syntax. So we define the complex gamma function, we prove various properties of it, and then we specialize it to the real gamma function. It's pretty easy to see that for real arguments, the function itself is also real, because all the things in the limit are real. And so we get a real gamma function. And so the idea is this is going to help us to generalize the domain in which we're thinking so that it makes sense to talk about limits. So using the gamma function, we basically define real analogues of factorials and binomial coefficients, just to make things a bit more intuitive and make it easier to mechanically translate between the naive integer versions and the rigorous real versions. So we define a function rfact, which is basically a real generalization of the factorial, which is just gamma of x plus 1. And similarly, we define a real binomial coefficient. Somewhat misleadingly, perhaps, I've called the parameters n and k, but they're actually real numbers, n and k, arbitrary real numbers. And the salient thing to notice is here we really are sometimes taking factorials of negative integers in general, or the negative numbers in general. So without a limit argument, this still doesn't help us because the gamma function isn't defined at negative integers. However, it turns out that as limits, these things behave beautifully. So specifically, we have the following theorem. That if you have two sequences of real numbers, nn and kk, which tend to two natural numbers n and k, then the real binomial coefficient of those sequences tends to the natural number binom nk. For the regular case, where k is between 0 and n, that's maybe not very surprising. But what's really nice is that this also tends to 0 for all the other cases. So this really does give you the kind of equivalence between binomial coefficients and the factorial quotients in a certain sense.
Are you really using nets for convergence there?
Yes, that's right. So net is just an arbitrary. So this isn't necessarily a sequence, but imagine it as a sequence, but it can actually be an arbitrary net. Yeah, that's true. And so the nice thing about this is that doing it this way, we can pretty much justify all the so-called naive manipulations of Gutman's book presentation without doing any kind of case analysis. However, there is one more thing we need to figure out. In order to, so you remember the matrix argument, so the key that made the matrix argument work is firstly that the thing you're interested in establishing can be considered as a continuous function of the matrix. And second, that you can actually approach the matrix arbitrarily closely by a matrix with non-zero determinant. So here we need to do something analogous. We basically need to show that if you have a pair of natural numbers nk, or actually, let's say a pair of integers nk, to generalize things, then there is some way of tending towards that pair of points, while avoiding all the special values that might get in your way, like poles of the rational function. So one rather nice thing is that we can actually, once and for all, define a way of tending to that point that works for every possible application. Okay. So yeah, this is just in a bit more detail. So gamma function is undefined, or points where the gamma function recurrences, like gamma of x plus 1 over gamma to the x, gamma of x fail. And we also need to avoid any cases where the denominator of the rational function becomes 0. But what's nice about those is all the cases that are problematic are basically defined by a bivariate polynomial with rational coefficients, as one can easily see by looking at the most general example. So let's define that notion in whole. So I define in a slightly ugly way the notion of being a bivariate polynomial function. This is actually a somewhat ugly and unnatural definition, but it does have a couple of virtues which I'll come back to later. It basically says P is a rational, P, which is a function from reals cross reals to reals, is a rational polynomial function if there is a finite set S which is a subset of natural numbers times rationals. In other words, it's a finite set of triples, I, J, C, representing C times x to the I times y to the j. So it's a very sort of crude way of defining rational polynomials. But this has, crude as it is, this definition has two virtues. First, it's almost trivial to see that the set of rational polynomial functions is countable, because it's just the image of a countable set. The rationals are countable, the natural numbers are countable, so the Cartesian product is countable. And that is something we're going to use. It's also very easy to see that any specific function you had in mind is a rational polynomial just by kind of mapping it back into this representation. And so then I'm going to say that a particular pair, T, that's a pair of real numbers x, y, is ratty, which is sort of meaning it's on some algebraic variety of rational coefficients. The name's also meant to suggest it's kind of bad somehow, we want to avoid it. If there is some rational polynomial function of which this pair is a root, and of course the polynomial has to be non-trivial. We have to exclude 0 polynomials, obviously. Okay. So now the goal is to show that we can approach any integer pair nk using non-ratty pairs of reals. And that follows actually pretty straightforwardly from two theorems which I happened to, well, one of them I happen to have already got in Holite, and one was basically trivial. So one is that any non-trivial algebraic variety has non-empty interior. In other words, if f is a real polynomial function, which means basically it's a function from r to the n to r, that's a polynomial function of the coordinates of the input. So if f is a real polynomial function and it's non-trivial, that is, it isn't equal to c for every input, then the set of points such that fx equals c, considered as a subset of n-dimensional space, I mean here we're just using the two-dimensional case, but this is a bit more general, has empty interior. And I mean that's kind of easy to prove, I think. I forgot how to do it, it's easy. And I already had that theorem in Holbein, fortunately. I remember distinctly doing it on the train once to amuse myself. We need one other thing, which is basically, this is a kind of Baire type result, that if you have a countable collection of closed sets with empty interior, then the union of that family also has empty interior. And this is a pretty easy corollary of Baire's theorem in some form. So the nice thing is, if we put those together, we can avoid every possible algebraic variety that we might end up with, because each one has empty interior, and there are only countably many of them, so we can avoid them all. Very nice. So using that, we finally get an actual rigorous theorem that justifies the WZ method. This looks kind of disgusting, and I won't go into all the details, but so for example, the first assumption says that f has finite support, and then we have this magic function, double uppercase f, that tends to f as a limit, and then we have a whole bunch of other stuff. But the crucial thing is this thing. We need to prove the WZ pair property, which is this, only for pairs of real numbers that are not ratty. And that turns out to be very easy, because that avoids every possible thing that is actually a problem in practice, because they're always defined by rational polynomials. And then we assume that the trivial case of the sum is 1, and we can deduce that the sum is always 1. So for instance, if we apply this to doing the easy case of summing the first n, or n plus 1, I suppose, binomial coefficients, we can actually define the corresponding real functions, ff and rr, and then g is going to be ff times rr. And it's actually pretty easy to prove that we have the limit property. I guess I should have shown the definition of g, but it's just f times rr, right? And in order to use the topological arguments, I'm defining it as a function of complex numbers rather than as pairs of reals, but then you can map between positions using this complex constructor. So it's easy to show that the WZ paired property holds with several possible exceptions, that n is equal to minus 1, or n plus 1 is equal to k, or k plus 1 is equal to 0, or n is equal to k. So provided none of those things happen, we're fine. And of course, all of those things are just polynomials with rational coefficients, and therefore it's easy to see we never need to worry about this. So we can just do the naive thing. So we've tried a few examples by hand, so to speak. I mean, I don't mean pencil and paper, I mean in the theorem prover, but not completely automated. And the nice thing is that now, in this interpretation, they all work in the, so to speak, naive way. So you can exactly follow that naive recipe for simplifying that was given in the A equals B book, but actually now we have some clear semantics behind it. And indeed, most of the algebraic manipulations are completely routine to automate. It involves dealing with rational functions, but because we can pretty much make any assumption we like about certain things being non-zero, it's very easy to justify all of those, and we avoid any of the trouble points or singularities. Currently, I haven't automated the slightly fiddly bit of showing that g vanishes at one end or the other, but that's also pretty easy because it's a rational function multiple of f, and f by hypothesis has finite support, so one just needs to show that if you fix n, then as a polynomial in k, the denominator of the rational function must be bounded for sufficiently large k, and then it follows from the finite support for f. So that should be easy enough to do, I think. So that could be automated too. And so I believe this finally gives sort of satisfying understanding of what's really going on in this method, which looks very clear at first sight, but actually isn't. And so I think you could argue that this actually, justifies the WZ method more precisely. And as such, there's some real value in the formalization exercise, even if you're not personally interested in computing huge sums. Okay, and that's the end. Thank you.
Yeah, I think that should be something like that.
I think it may be right. There are lots of ways of reformulating it that on the face of it look slightly different, but basically because MO n plus 1 tends to 1, it's actually kind of sometimes indifferent which form you take. I mean, you may be right. I have made that mistake several times, but I think, you may be right, but
I just looked at this mathematics.
yeah. I think I copy-pasted it directly from Hall. So assuming I didn't make a copy-paste error, I feel fairly confident that this one is right. If that does indeed say exactly the same as that, which it seems to. So I think it probably is right. But yeah, you're right. I have managed to confuse myself many times over that issue, because some books do take a product from one, and then you have to kind of remap it, but you basically just get a factor n plus 1 over n, so it still tends to the same levels.
It was gamma 1 plus n over n.
Okay.
Sorry about that. That was my fault.
Okay.
I can always ask one. So do you think Doron wouldn't say, well, come on, I always have this in mind, like this is a trivial way how to generalize the factorial function. Every mathematician knows it. And
That's possible, actually. So that's an interesting question, whether there is some kind of guild of people who just think this way. I mean, if you think about hypergeometric functions more generally, then in some sense you're always thinking of these things maybe as functions in the complex domain or something. But the thing is that point of view is completely invisible in the standard presentations, but it may be that they have that in mind anyway. I mean, even in some sense, even to say that the binomial coefficients are hypergeometric, you need to hedge, because if you're defining it in the combinatorial way, strange things happen once you go off the k equals 0 to n. So even to say that it's hypergeometric is kind of already making some kind of assumption like this, perhaps. So I think I don't think I've discovered something that is unknown to people. It's just I have discovered something that is not made explicit in the elementary presentations.
Yeah. So I was kind of wondering how quickly he would dismiss you, because I saw this dismissing talk in Paris 4 years ago when he was bashing Tom Hales for losing his talent and doing things like this. So you could try to ask him, could you please specify this fully formally, and then compare it with your presentation, whether he would offer the same kind of formalization as you did, or whether he would just dismiss it completely.
Yeah, I really don't know. I've never seen anything in Zalberger's own writings that was like this. I have seen a paper by Ira Gessel that is the closest I've seen to this, where he is explicitly considering gamma functions and limits, though I'm not sure if the details are quite the same.